Okay guys, we're going to continue our exploration of topic 4, stoichiometry today. We're going to be getting into solutions. You're going to find that a large part of chemistry deals with reactions that are happening in solution. So let's get to it. First off, we have to understand what solutions are. Volumetric analysis is kind of a general specific heading that we give to this. Any kind of analysis of chemical reactions where you're dealing with volumes of liquid, volumetric. Okay, so again, many of these reactions happen in water. We're going to start off first by defining a solution is equal to the solute, and the solute, this is the piece that looks like it disappears. Okay, so the solute seems to disappear. Then we combine this with the solvent. The solvent is always the substance that is in larger amounts. In most cases, we're going to be thinking of water as our solvent, in which case we call this an aqueous solution. Okay, so solute, typically this is going to be a solid that goes into a liquid solution in our terms, but you could have solutes that are not necessarily in the solid state. So solute plus solvent makes a solution. We can express the concentration of a solution, and concentration basically just means how much of the solute is present, okay, in relative terms. So do you have a high concentration or a low concentration relative to something else? Now, there are two common ways of presenting this. You can either have grams per some volume of solution, or you could have moles per some volume of solution as well. These are our typical units, the final units. Again, grams per liter, volume unit, or grams per milliliter. These two are common. We also have moles per liter, which we're going to be getting to now. So our most common way of expressing concentration is known as molarity. We say it's probably the most useful way because what molarity tells us is the actual counted number of particles, right? It's related to the actual counted number of particles, which is more valuable than having grams, which is just related to some mass standard. So if we were given a solution, so let's say the solution concentration was 0.250 moles per liter, we would say, we express this in a specific terminology. We say that this is 0.250 with a capital M, and this is said 0.25 molar solution. Okay, so this capital M refers to the moles per liter, and we call this the molarity. It is a molar solution of whatever kind. So when we say molar, this is a description of the concentration. One thing that I do want you to be familiar with is the shorthand form of this relationship, though. So we say that the molarity, okay, so molarity, capital M molarity, is equal to the number of moles. Okay, so I give moles gets the lowercase n letter. This represents the number of moles divided by the volume in liters. Okay, so this must be specifically in liters. Now, what we do with this is we actually typically rearrange it. We're going to put this together as moles. So n, which is again the number of moles, is equal to the concentration. Okay, so the molarity, which we again say this is the number of moles per liter, times the volume, and again this must be in liters. So if you look at the units, you'll notice again moles is equal to moles per liter times liter. Liters cancel, we'll get our moles here. Now let's go ahead and practice a couple of tasks here. So first off, the question is asking what mass of solute, so this is solid sodium carbonate, must be used in order to prepare 275 milliliters of a 1.20 moles per liter sodium carbonate solution. So let me go ahead and get this one started. We're going to ape this as you want to remember, analyze, plan, and evaluate. Ape these. So we're going to analyze. First off, we want to know what mass of solute. Okay, so the mass of the solute we need to know the need would be how many grams of the solute, in this case, solid sodium carbonate. Sodium carbonate would be Na2CO3. So what mass of solid sodium carbonate must be used in order to prepare 275 milliliters, we see this is a volume, of a 1.20 mole per liter sodium carbonate solution. So these are our have information, right? We have, it will be 275 milliliters of solution, and then we need a 1.20 molar concentration of that solution. So to do this, there are a couple things that we're going to have to keep in mind. First off, the relationship between the solute and the solvent. When we have a molarity, again recall that the molarity is equal to moles of solute divided by liters of solution. So we have a couple things that we have to keep in mind here. The first is that this is in milliliters. We're going to have to do a conversion, which you can do as a decimal shift or dimensional analysis. You know that milliliters, there are 1,000 milliliters in 1 liter. So we've got a shift of 3. We see that that is 0.275 liters. Now, in addition to this, so our volume is going to be good. Our molarity is now good. But what this equation does is it gives us the number of moles. We need the number of grams. So again, we're in the planning phases right now, getting everything set the way that we need it. We're going to be able to determine the number of moles. However, we're going to have to convert using molar mass in order to get from the number of moles into the number of grams. So let's go ahead and work this one out. The first thing is, again, plug in for our molarity, 1.20 moles per liter. Okay, note that I'm putting the actual units here. These moles per liter, if I rearrange this equation, it's molarity times the volume. So molarity times the volume, which was 0.275 liters. This is going to equal my number of moles. So 1.20, here I'll calculate this over here on the side. 1.2 times 0.275. This gives me 0.330 to 3 sig figs. 0.330 moles of the solute, which is, again in this case, Na2CO3. So now our second step is, again, using our molar mass. We got to consider molar mass of Na2CO3 in simplified terms, okay, because we can do approximations here. Sodium, Na, is 23, and we're going to do that times 2, gives us 46. Then carbon is, in simple terms, 12, so carry that over. And then oxygen is 16. Multiply that one by 3, we get 48. So combining the sum of all of these relative masses, we see that we've got 48, 50, 60, 106. So there are 106 grams per mole of Na2CO3. So we can apply this here now as 0.330 moles of Na2CO3. And then we want to cancel, again, we get rid of moles of Na2CO3 to find the number of grams. And so that's going to be the molar mass, 106 grams per mole of Na2CO3. So I will again calculate this over here by, and again it's multiply the top, divide by the bottom. So let's see, we get 34.98, so that's going to round to 35.0 grams of Na2CO3. Okay, now let's go ahead and take a look at your next task. I'm not going to work this one out fully, but I will give you a heads up. This one is definitely a more complicated problem. What we'd want to do is take a look. It says a sample of copper 2 sulfate pentahydrate. Recall, copper 2 sulfate, so CuSO4, and it's pentahydrate. The penta indicates 5H2O. So this compound has a mass of 8.512 grams. So you're going to have to figure out, well, based on this number of grams, what is the number of grams that is just copper sulfate? Because when preparing a solution, you're going to have to just factor in the solute, and this H2O is no longer going to be bound in the crystal. So be aware, a crystal with a mass of 8.512 grams is dissolved in 500 milliliters of water. Okay? A 25 milliliter portion completely reacts with 20 mils of a 0.1702 mole per liter solution of iodide ions. So the iodide ions, I1 minus ions. In what molar ratio do the Cu2 plus and the iodide ions react? So you'll have to, again, think, based on whatever the molarity of this is, it's the same number of moles of copper 2 plus when this dissociates. So again, this one's going to be more involved. You are going to have to consider that you've got a 25.00 milliliter copper sulfate solution, so this new copper sulfate being mixed with 20 mils of the iodide ions. So copper ions, 25 mils of the solution of copper ions with 20 mils of our solution of iodide, and then do a comparison, kind of like when we did percent composition, where you find the total number of moles and then you divide those number of moles by the smallest number. So hopefully you guys make some progress on that one. You can always shoot questions out to me on Facebook. Now, for question 3, here carbonates in the form of antacid tablets can be used to neutralize stomach acids. We're given 25 mils of a 0.1 molar sodium carbonate solution, so concentration times volume once those are converted properly. So we can find the number of moles, and this reacts with 35.3 mils of HCl in a simulated neutralization that we have here. So the question is, what is the concentration of our acid? So we're going to have to compare the carbonate concentration to the hydrochloric acid volume, knowing that we need the same number of moles of each of the acid and the base. Okay, so again, play with that one. Hopefully it makes some sense and give me your answers on the online assignment. Now, some metals will react vigorously with acids to produce hydrogen gas. What mass of zinc metal will react completely with 75 mils of a 0.2 molar sulfuric acid? So maybe I should also bring your attention to this part. Again, these 3 questions require that you first have a balanced equation. So you're going to have to use those skills of converting your names using nomenclature to make balanced compounds and then balance these equations. I'll go ahead and work through that real quick on this one, but let you finish it on your own. So it's saying that metals will react vigorously with acids to produce hydrogen gas. We have zinc metal, so zinc metal. So this is a solid zinc sample reacting with sulfuric acid. So we have H2SO4 aqueous. And that is going to produce hydrogen gas, it says. So that's going to be H2 gas. We'll go ahead and do our simple balancing. We see here the zinc is going to kick out the H2 like so. So the other thing that is going to be necessary is we're going to form a compound of zinc sulfate in solution. So ZnSO4 aqueous. And we see this works because zinc is going to form a 2+ ion to bump out these 2 positive hydrogens. So I will let you continue on that on your own, solving the problem based on that equation. Now, here we have our hydroxides being used to neutralize again. This time I'll just let you work this one out. Alright, now we are going to get into a concept that is called molality. This is another concentration ratio. Be aware, even though the words look similar, it's not the same as molarity. We'll talk about that now. So this time, instead of taking the number of moles divided by the liters, we're looking at the moles of solute divided by kilograms of just the solvent in this case, okay? So not the overall solution, but just kilograms of the solvent itself. So the purpose of this is that there are some processes where the volume can actually change, and that would affect your molar concentration if you have some kind of reaction that has massive heat changes. So in simplified terms, this is our molality equation. Molality is moles of solute divided by mass of solvent in kilograms. So here's an example problem of that. Question is, what is the molality of a solution containing 35 grams of sodium chloride in 2,000 grams of water? So this must be the solute, it's a smaller number. 35 grams of the sodium chloride in 2,000 grams of water. We're going to have to convert these 2,000 grams to kilograms and convert these grams into moles using molar mass, but you guys can handle that. Now, a solution of 6.1224 molar sulfuric acid has a density of 1.3028 grams per milliliter. We are tasked to calculate the molality of the solution. So again, we're going to analyze, plan, and execute it. Okay, so with our analysis, we're going to see here we have 6.1224 molar sulfuric acid. Okay, so this again, 6.1224. This is in the unit moles per liter, so I'm going to write this as a fraction this time, per 1 liter. And this is the sulfuric acid, right? Well, the sulfuric acid isn't changing throughout the solution, so I'm going to leave this off just for the sake of simplified calculation. Now, the density is also given to us as 1.3028 grams per milliliter. So I know the moles per liter and I know the grams per milliliter, but the question is asking what is the molality. So the end goal, the need if you will, is to determine what is the number of moles of solute divided by kilograms of solvent. So what we can do with this is we can actually set this up so that the correct units cancel. We'll have 6.1224 moles on top, and we'll have our liters on bottom, 1 liter. Now, the initial thing to cancel, we don't want to mess with moles, but we do want to get the bottom portion to be kilograms of solvent. So our planning steps we're going to see here, from liters, we need to get into kilograms, and we're given a density which is grams per milliliter. I can go from liters into milliliters, and this relationship will convert milliliters to grams directly, okay? And then I'll need to be able to convert grams into kilograms. So I'll show you what that looks like. Here I've got my liters, and 1 liter, if I need to get to milliliters, is 1,000 milliliters. Then the upstroke cancellation shows you liters cancel here. Now I have milliliters. I need to get rid of these milliliters using my density this time to get into grams. So it is 1 milliliter for 1.3028 grams. So that's our way of expressing this density in terms of a conversion factor. So this is going to cancel now my milliliters. And the final thing is that I don't need moles per gram, I'm going to need moles per kilogram. So 1,000 grams are equal to 1 kilogram. And now the grams will cancel. So we've got our moles per kilogram using density as a conversion factor here. So when I do the math on this, again, it's going to be top times top times top times top, divide bottom, divide bottom, divide bottom, divide bottom. But you'll notice that you've got 1,000 divided by 1,000, so that calculation essentially cancels itself out. So it's going to be 6.1224 divided by 1.3028. And I did this calculation earlier. Let me just find the results of that, and you can check it on your end. The molality should be, if we assume, let's see, yes, we're not going to deal with molar mass on this one. It's going to be 4.6994. So 4.6994 And the unit for this, again, this is molality, so it's moles per kilogram. Moles per kilogram. Also, one thing that you can be aware of is that another way of expressing this, before, you know how we had molarity as capital M? Molality could be expressed as italicized lowercase m. So this would be the symbol. It is 4.6994 molal sulfuric acid solution. So that's my H2SO4. Okay. Now let's talk dilutions. So much of the time you'll have solutions that start out as a concentrated stock solution, and you dilute them in water, make them less concentrated. So an example of this is, you may need a 2 molar solution, and you might need exactly 4 liters of that solution. So if you begin with a 10 molar solution, you can use stoichiometry to convert into the appropriate volume here and make that solution. So the first step in preparing these solutions is you need to calculate the number of moles present in the final solution using our moles equals concentration times volume. And again, remember, this is a modified version of the molarity equation. Molarity equals moles over volume in liters. So moles equals concentration, and again, this is molar concentration, moles per liter, and volume in liters. So if we were given that previous example, 4 liters of a 2 molar hydrochloric acid, let's say, is required for an experiment, what volume of a 10 molar hydrochloric must be diluted with water? So we're going to say that the moles that we need, the final moles that we need, are going to be equal to the concentration, so 2.0 moles per liter, multiplied by our volume, 4.0 liters. So do the math here, you get that liters will cancel, you'll have moles, and it's 2 times 4 is 8.0 moles of my hydrochloric acid solution. Now, we are going to do our second step. Is now that I know the number of moles of the final solution, I'm going to use the same number of moles in the initial calculation. Okay, so since I determined that I have 8 moles, I can plug in the new concentration. Okay, so, or I should say the original starting concentration here, 10.0 moles per liter, multiplied by the volume. If I rearrange this, what you're going to see is I have 8.0 moles, and I would have to divide that to get this V isolated, divided by 10.0 moles per liter. Moles will then cancel. 8 over 10 is going to be 0.8, 0.80 to have a second. Okay, so 0.80, and notice it's going to be 1 over per liter, or 1 over 1 over liter, which is just liters. So this is the volume that I need. This is the volume of my acid, my concentrated HCl solution. Now, I will tell you, when you have dilutions, one simple way that you can also see this is using the equation M1V1 equals M2V2. This essentially puts this relationship together directly, so that you see concentration times volume equals concentration times volume. Basically, we're taking moles out of the picture by putting these things together, and that's actually a pretty easy way of remembering how to do a dilution calculation. Let's go ahead and get into the third thing. The last component, of course, is you have to do a dilution by including water, and the volume of water added is the difference between the final volume of solution and the volume of the concentrated solution that's being added. So basically, in practical terms, we can find a number for this, but in practical terms, really you're just going to fill water up to the appropriate level of whatever the container that you're diluting it in. Okay, so if you know what the final volume is going to be, just have containers that are large enough to have some kind of a tick mark at that level. Typically we use volumetric flasks, and we'll get into that more later. Now, here you have some tasks. You can work on these on your own for you to calculate the volume of the 3.25 molar nitric acid. with a 500 mil, or that will make a 500 mil 1.25 nitric acid. Also calculate the volume of 2.6 molar potassium hydroxide that would be diluted with water to make a 250 mil 2 molar potassium hydroxide solution. Third one is what volume must be added to a 4 molar hydrochloric to produce 2 liters of a 0.5 molar hydrochloric. And then I've got one last thing, a safety note. You know how I said you're going to be adding water to that line for your final mixture? Well, that's only kind of correct. One thing you really need to be aware of is that it can be dangerous dealing with acids. Specifically, if you add water to an acid, we have an exothermic reaction, which means it releases a lot of energy, a lot of heat. So what we're going to want to do in that situation is just be aware of it. We could potentially cause, in certain cases, certain acids that are very strong will cause the water to boil because so much energy is being released, which can cause splashes and spills of boiling acid. Bad situation, right? So the thing that you need to be aware of is you always add acid when doing your dilutions. Okay. So again, if you have any notes or any questions on these notes, feel free to hit me up via email or Facebook, and hopefully that all made some sense.